today I'm talking about what Tim and I decided to call the anatomy of a blockchain. So I put in here at the bottom not PhD because I actually do not have like a formal training in like a master's or PhD. I've been a practitioner, let's say, for the last 7 or 8 years now. I think with a lot of the research, you read a paper and you're like, oh, obvious, the results are amazing, I'm just going to throw out everything and re-implement this. Or, oh, I'm only going to focus on consensus because that's like the most important part of the system, and everything else kind of that's like solved problems, let's not worry about it at all. And so with today's talk, I thought, what would be fun if we just built a blockchain together from nothing? Because I think sometimes, at least if you've taken like an operating systems course, you often ask the question, like, how deep can you go? It seems like there's always another layer beneath. And so what if we go all the way down, and then we go up and decide how to think about some of these decisions on how to actually design one of these. So this talk, I don't really know how it's going to go, to be honest with you. It's a lot of slides I'm presenting for the first time, so if you have any questions or not something I say doesn't make a lot of sense, let me know. It's a kind of a combo between a survey of what people do and then also kind of some of the fundamental things you need to be thinking about when you design some of these systems. So the other caveat I will give you is really this is more of a conversation around how to design them or how to build like a modern blockchain. So I think of it more from like the proof of stake lens rather than something from maybe the proof of work lens, which I have not seen a proof of work chain go live in a while, other than maybe Nock chain, I think, which is the most recent, at least that I'm aware of. So step one, I think makes a lot of sense. You know, you define your participants. I think the way that crypto was first explained to me, which I still resonate strong, is you have a bunch of random people on the internet and you want to figure out how to do something together. You don't know each other and you assume some amount of them are honest. And I think that's a really fun computer science problem. And I think if you start from there, you can kind of think about how and why you would make some of these decisions. So let's assume that we have a bunch of participants. They have a public key and some sort of identifier on the network layer. We'll just say an IP address for now. The first thing you got to do is figure out how you want to actually connect to each other. So this may seem like when you're in consensus land, oh, there's some sort of like abstract P2P system that like messages kind of go across. There's actually a lot of nuance here. Different networks do very different things. So I think in the early days, it was pretty heavy on the TCP side. And then in recent years, people have kind of started to explore the UDP and quick world because they want to get out of the kernel as much as possible, because obviously we can all outsmart the kernel. And so the first kind of survey there gets into some stuff like the Anza and the Solana team has done, where they started with UDP and then migrated to Quick to give some sort of authentication on the stream. But the interesting thing that has also come out lately is turns out TCP can actually be made very good, very close to the performance of like a UDP and Quick setup, and then you benefit from everything that you already know about TCP, which is that you have, obviously the core of TCP is the congestion control algorithm, and for a while we've been using like Cubic, Reno, whatever. Those are really bad, it turns out, for a number of different reasons, but there's something that came out a few years ago out of Google called BBR. And to be honest with you, I don't remember what BBR stands for, but it's BBR. And it's been mainlined into the Linux kernel for about 5 years. And it's a totally different way to think about congestion control with TCP. And it turns out that it hits what is pretty close to optimal result on like a channel up to like some pretty insane loss rates. So the graph on the left you can see here is basically Cubic and Reno, which degrade significantly as soon as you start to lose almost any packets. There's also a pretty slow warm-up period, so you may feel like you have like a 10 gigabit connection or even a 50 gigabit connection, and you're using a fraction of that, even if you're losing like 0.01 like packets. Cubic and Reno kind of fall into that camp, and then BBR, and there's been a few different variants trying to kind of model the problem a little differently, end up getting within like 80 to 90% of the optimal path. But the benefit is, again, you retain like this native stream semantic, and then the kernel just manages it. So if you're running on Linux, you can just flip a little switch and just enable it. So it's pretty nice. Credit to Celestia for discovering this, or rediscovering it, as we do in crypto. And so you can just enable that. So a number of networks now run with that. Tempo, for example, runs with this, and it's been pretty efficient. The other thing that I think some people get a little over preoccupied about is this notion of like head of line blocking. I think if you start to think about a node having limited bandwidth, head-of-line blocking is just a kind of a natural consequence of having to deal with like a limited set of resources. And you may actually not want to have a bunch of channels that you don't really control the ordering of taking up your bandwidth when you don't expect it. So we actually don't worry too much about trying to have multiple channels that like kind of run over the same thing. We have one thing we want to send the most right now, and we want to use all of our bandwidth to do that. Okay, so we have public keys. We have some way to connect each other. That connection, as one of the speakers a few days ago mentioned, is a lot maybe less stable or like less secure than you think it is. So the next thing you're going to want to do is authenticate that connection and optionally encrypt it. So there's a lot of ways to do this, and it's changed a lot over the years. The standard most people use today is some form of like a Diffie-Hellman, and then you use some sort of stream cipher like AES or Cha-Cha, and a lot of that is today like built into some pretty popular protocols you may have heard about, like Noise Protocol, or obviously like some sort of TLS kind of handshake stream construction. And the funny thing is, I think it's something that you again kind of just pick and like, oh, I'll just import this like noise library, or I'll like import this thing. There's actually a lot of complexity that goes on under the hood in these protocols that can dramatically impact your attack surface as a node. So some of these things are not really meant for like super adversarial environments where people are trying to open connections and like keep you in the handshake as long as possible, or like try to like spam you during the initial handshake. And remember, if you're authenticating like this, usually that means there's like someone on the other side that has a public key, so you have to verify some signatures too. So depending on what signature scheme you're using here, it can actually dramatically impact your resilience. So a lot of teams will actually not use these and roll their own. We are obviously no exception to that. But here are some of the properties that we found at least useful when thinking about how to do this. So you want to have some sort of like mutual authentication. You want to have some sort of like ephemeral secret key that you don't have to worry about, because it's a very hot key, right? So you don't want to be using it all the time. Hopefully you can just discard it and be done with it. Very strict understanding of timeouts and like kind of how the stream behaves under very specific conditions. And then you can actually dramatically simplify a lot of how you think about the stream if you already assume you're in this P2P network where like the people already know who is actually a validator, and sometimes even what their IP address is. Because a lot of the traditional protocols, maybe even Noise, for example, they have all sorts of ways where you're trying to almost like hide the participants doing the handshake. And so in some of these systems, it doesn't really make a whole lot of sense if you already know who the peer set is. And then same thing with like zero RTT, like it's not like a client-server relationship. These are like kind of a communication of equals. So you may want to think differently about how you actually construct the stream. And then the big thing that actually comes into this a lot is most of the streams you can take off the shelf have very specific assumptions around what certificates you can actually use on both sides to authenticate each other. So if you're familiar with like TLS and like X509 certificates, you'd be like, can't be that bad. It can be that bad, yeah. So at Avalanche, and this was a little bit before my time, but the way that staking worked is because it was such a network-heavy protocol, the node ID of all the participants was actually just a hash of their staking certificate. So it's a 20-byte hash. It's just a hash of a self-signed TLS certificate, because it's like, oh yeah, we'll just use like obviously all this stuff that comes with Golang. Why would we have to do our own? Much of my life has been spent dealing with this problem. And so another thing that I think is something that a lot of teams consider, and something we've also done, is if you actually define your own stream protocol, you can have it with a very simple handshake message that just uses like your native staking keys directly. So you don't really have to worry about a translation between two layers of keys where you have like a network key and the staking key. And then there's a whole balance and conversation around how to think about anonymity on the peering layer. We have strong ideas on that around that you don't need that, but go ahead. Yeah.
Can you give an indication of why you would suggest to use a single key staking in networking? Because every time I try to have that argument, I lost.
I'll show you in a few slides. Yeah. Yeah. And that's one of the big ones we've seen is like, yeah, I'll get into this in a few slides, but in our mind, like an open P2P network where you have no connection between the staking set and like who's on the peering layer actually works a lot better for proof of work, where you don't actually know who's going to produce the next block. So the most efficient topology is just for people to be randomly connected and then propagate. But if you know the full set, knowing the actual participants means that you can skip like 99% of handshakes. You can just do handshakes with people you know, and then also from IP addresses you know. But we'll get into that now that we have some sort of stream that we actually have. Oh yeah, sorry, go ahead.
You're going to talk about the denial of service?
All the way up. Oh yeah. Yeah, so I'll get into that in like when we talk about some of the actually connecting to like a broader network, because the first construction we care about is just being able to have one connection between two participants. And now once we have a connection between participants, we want to think about how do we discover other people in the network, or like where we source that information for who to connect, and then how to secure those connections, yeah.
And okay, like this easiest thing would be like just TLS with pin certificates. Like instead of reinventing everything and maintaining code base.
So I mean, I think what we think about a lot is how small do you want your trusted computing base to be, and like, do you want to maintain that code, or do you want to trust someone else to maintain that code? Yeah, so we don't use TLS at all, just remove it all. And so like our whole stream cipher and handshake is probably 1,000 lines of code, 2,000 lines of code. So like the point of this conversation is not to tell you how to do anything, just to say like, if you're going to do it, just know that taking something off the shelf may not be perfectly geared for like a P2P environment, especially an adversarial one, but implementing your own stream, very difficult to get right if you want all of the properties that you can get out of noise or TLS. And I think the claim we would make is you don't need all of those properties in a lot of these networks. And if you instead like whittle it down to just what you need, the actual stream protocol can become quite simple. And for us, simple means easy to analyze, really the attack surface of is what we care about. How long can you keep certain phases of the connection open? How strict can you be about like the timeouts of different parts? Yeah.
In some environments, people just like to have NIST-approved streams and so on.
Yep.
NIST-approved countries. So there's an advantage of using kind of a standard language.
Yeah. Yeah. I don't want the point of this talk to be like, go roll everything on your own. For example, we don't touch like AES or Cha-Cha. We'll just use that as is. Yeah, we don't do our own.
Why not?
Yeah, I know. Well, so like there's some places where it doesn't make any sense to like tweak it in that way, but then there are some places where you can remove we feel a lot of complexity in like some algorithm or mechanical steps by simplifying the state diagram. So like the one thing is like we always do, it's at most one back and forth. There's never more steps than that in setting up a handshake. And then at the same time, before you actually will even attempt to authenticate, we can check a number of different things to make sure the handshake's even worth attempting. And I think that there's a lot of metrics to care about here, but a lot of times for us, it's like how many people can you actually churn through per second when we're talking about like DOS. And what we have found is like our protocol construction and like the way the stream works, much faster than what you would have for a traditional thing. So really all of this complexity is born from performance, I would say, is probably the unfortunate truth many times. We can get into more of this, yeah.
Actually, a quick follow-up. Do you know by any chance who or in which setting people are actually using TLS rather than roam stream? Because every protocol that I know that use TLS eventually switch to their own stream.
Well, I know Avalanche still does. I don't know others off the top of my head, no.
So it's quite a pattern. I mean,
yeah, I think I don't know if that's really a question of like not using TLS as much as it is some teams getting pretty excited about using some form of like UDP where you don't really have maybe the same authentication. And then a lot of teams have gone from that into something authenticated, and then when they do that, they do some other sort of scheme to try and use the staking key on the P2P layer because they don't have...
Okay, so that's interesting. My intuition always means because TLS was unmanageable. It was not really designed for P2P networks. People try to put it because it was box, and now they realize that actually it's just not worth it. But you're saying maybe it's different. Maybe it's just like the fun of implementing your own stream.
I think it's just that if you can see, you want the dumbest thing you can get away with. That's how I think about protocol design. And so sometimes a lot of this stuff is way too complicated for what you actually need. And I think the question is, do you trust that you can actually implement it well enough yourself that it is secure, and is it code you want to maintain, or is what's off the shelf available? So like in libp2p, for example, they offer a few different options, both noise and self-signed TLS certificates. To my knowledge, most people use self-signed TLS certificates in libp2p. So, but yeah, let's keep going. The next question, right, is like now you have this authenticated connection between two people. Now you need to figure out who else is in the network. So usually, again, in proof of stake, you have some list of the participants, at least their public keys. You may not have their IP addresses, and you maybe want to discover those dynamically. So the first option is you do that. So maybe when you have the binary, there's some initial set of participants you should connect to, whether those are like DNS entries that are updated in some way, that's common like Bitcoin and Ethereum, or it's like hard-coded public keys and IP addresses. And then once you connect to those would typically be called like bootstrappers. You then gossip information between them. The really cool trick, if you have a known set of participants at some epoch or something like that, is that you can use bitmaps to like very efficiently communicate your knowledge of the peer set. And then when you basically exchange discovery messages with different peers, they can just send you basically signed IP records from those peers, who else to connect to. Now, this is nice if you like don't want to have a list of the public key and IPs somewhere. It's really nice though if you're open to that idea, where you actually know all the public keys and IP addresses of the participants, and like that synchronized map, just imagine is a log, and that log is a chain. We'll get to that later. And the really big win there, which comes back to your question, is if you know all the IP addresses and you know all the public keys, it becomes really easy to be pretty robust. And so this is what we typically recommend to most teams today. And most teams are using this sort of construction, at least the ones that we talk to. And you just have like a little script that runs next to your node or even in the node, and then you update basically your kernel's IP tables, and you won't even entertain TCP handshakes. And then remember, you already control how you're doing the actual handshake of the stream and the signature verification, everything that comes with that. So you're already limited, but this is great because then you can just push that complexity of being DOSed up to the cloud, who can then firewall way better than any binary ever could. Yeah.
I'll just suggest one test, which is you take one of these fully authenticated clients, and just the way you make it behave in a malicious way is just to bombard everybody else.
Yeah.
Let's try that.
Yeah. Yeah. So we I think the thing I'm not talking about in this session is kind of how you approach like chaos testing, Byzantine testing, and just general testing altogether. From the beginning, we've built this deterministic simulation testing framework. So everything we do is deterministically simulatable. So we have our own runtime with time, randomness, and everything. And so we first will like test correctness and test all sorts of really funky scenarios to kind of see how it performs. And then we have a few phases of these like kind of what we'll call like DOS or chaos networks, where you then attempt to blow up everybody else. But the big thing you have to think about in this world is really back pressure and how you think about rate limiting. So just because they're a peer doesn't mean they're your friend. And so they could really, really push you, so you have to be careful to control how much data you're willing to read off the wire and at what time. And then how do you ensure fairness? This becomes very difficult if you have like a non-uniformly weighted staking set, because then it's like, okay, well, should people that are not, that have more stake be given more rate limit, because technically they're like more important to the network. But if you have symmetric traffic, maybe not. So it's just something you have to think about as you design these P2P networks, is really rate limiting this fundamental concept and like kind of how you give people the opportunity. And the problem is you can go all the way and say like, oh, I'm going to rate limit every connection's CPU, I'm going to limit their RAM, rate limit their disk usage, or you can just say how many messages you're willing to process and just assume that that's fair and that it like amortizes well across all the messages handled. You got to be careful, like in most adversarial environments, where if your rate limiting tracking becomes more expensive than just handling the message, you got to maybe take it back a step. So there's a lot of balance here, but it's very important to think about how adversarial peers can really undermine the performance of your system. Yeah.
In practice, sometimes we have boot nodes to discover peers around the network. Do you have this design? And if not, what's the trade-off?
Yeah, so this would be what I call the kind of option A, which is you don't actually know all the IPs when you sign up, but maybe you know the participants. And that would be like boot nodes, bootstrappers, whatever you want to call them. And then that's how you initialize and connect to some people. And then from there, you then start to learn about everybody else. The real thing that it comes down to is DOS resilience. Because you don't know all the IPs that you're going to connect to or that will connect to you, you have to accept and consider many more connections. And so you know, you can have a binary in a machine that can process a lot of messages, but there's always an amount a botnet can send that exceeds whatever that is. I can assure you that. And so if you can instead push like the rate limiting and firewall problem up a layer, you can have a lot stronger guarantees on the resilience of things. Funny enough, like for a lot of really professional validators, I mean, that's inherent to any system they run. Like you have all sorts of firewalls set up. So it's not a crazy concept. In fact, they're more concerned about something like this than they are about you telling them, oh yeah, here's the IP list. It updates every few days when the epoch changes. Make sure you're up to date, otherwise you're not going to connect to all the peers. And they're like, okay, they understand that. They don't understand this whole like, oh, anyone can dial you. Because they want to, like their security teams are always like, you know, what are these IPs? Like this IP is associated with North Korea. This one's like, why are we letting these people connect to our infrastructure? So having a very strict list of who can connect to you actually becomes, it makes them more comfortable, put it that way. There's robustness questions there, because if the log halts and you need to rotate IP addresses, you then have to distribute potentially like a static list of IP addresses. If maybe I think a year and a half ago, like Hetzner kicked off all the Solana nodes with really no warning, and then the network had to like reposition a lot of that stake very quickly. And so you can imagine if instead of 20%, they kicked off 50% or something like that, you may not be able to actually update those IP addresses, and the chain would halt unless you distributed something. So that I would say is the other big downside of keeping track of like the public key IP map is that, yeah. Yeah.
Yeah, I think you kind of reply. So when you change the address of specific to a key,
yeah.
You are, I don't know, you have a count or something like that. So
can you say it one more time? Sorry, I didn't catch the beginning. Yeah.
Sorry, when you have an IP, so you have a public key, you have an IP, and
yep.
you update the IP for any reason.
Yep.
How this propagates through the network, and how will you keep track of what's the newest?
Yeah, so we use, in this setting, most people that use this use the actual chain to communicate this and synchronize it. There's no like extra system that tracks that. If you wanted to do it, it needs to be synchronized. Otherwise, you're going to have people that can't connect to each other. So you would need some sort of reliable broadcast or something like that, or some way to communicate with some notice, like, hey, every 7 days we're going to refresh our IP maps, and then like make sure you some sort of like off-chain process or something like that. But most teams I've seen that do this use the chain in some form for this. Yeah. So like. It's weird. Some people are like, I don't like the idea of putting all the public keys and IPs on, like everyone can see. And my response to that is like, trust me, the firewall's fine. Like you'll be safe. It's safer this way, actually.
You're kind of pushing the problem to the consensus layer.
I think that's a reoccurring theme in much of the stacks these days. Is like you need agreement and synchronization. You already have agreement and synchronization somewhere. If you can make it work, it can solve a lot of problems. Which is a great transition. Well, do you mind if we keep going, or I just want to make sure we have enough time?
I guess the question is like if the IPs are on the chain, and you need to discover peers first to see the chain. So.
Yeah, so there's you often what you'll do is you'll have some sort of like startup condition where either you have a Genesis file that has some set of public keys and IPs to start off with. If there's no more coverage on that anymore, you can't start because whoever you're talking to. Usually what you'll do though is you'll have a finalization certificate from some point in the future, and that finalization certificate will be accompanied by some set of like some block that has the current list or within some recent time. What a lot of teams will do though is like when you cut a release every 2 to 4 weeks, you'll put a list of like the latest there. That also kind of helps ground truth a bit, the system, depending on what your certificate scheme is. That can actually give you some additional assurance. And so as long as you don't have too much churn from the time you have that binary to the latest release, a new node can start up pretty reliably. Yeah, but there's an initial discovery problem where we prefer not trusting like an IP or like a API or network for that, and instead distributing that as part of the binary. Yeah. Yeah.
For that topic, so the one pattern I saw is that basically these validators have they're a validator and a client. So when they start as a client. They sign with their validation key, and then as a client they kind of push to the consensus, here's my IP. It also helps you if you lose your IP, right? If there's a problem. Yeah. Your client is still working, and you can kind of, as a client, sign with your validator key.
Yep.
Saying, hey, I have a network problem, keep changing, whatever.
Yeah, so there's sometimes there's like an admin kind of like manager. It's like a lot of how this is managed, because it's on chain, ends up sometimes flowing into the execution layer and like how you actually want to manage the configuration of this information. So in Tempo, they have like a precompiled staking contract where people like can submit via some sort of multi-sig, like what their latest like IP address is, or like kind of their validator keys, and you can have like whitelists and various like staking controls on it. But yeah, the execution layer is maybe where you give it a specific form, but then the execution is just kind of, it's a problem up there, just like as you process the log, how you actually want to determine what the latest is and just make sure everyone agrees on it. So yeah, I think people change a lot based on what happens up there. Yeah. All right, so we've got a network, and now the question is, what next? Well, we really want to agree on something. We really want to agree on the dumbest possible thing, which is just one digest. So the consensus problem, I think, over the years, because there's so many things you need to solve, has sometimes become a much broader conversation of, well, you need a contiguous log, you need to like think about transaction validity in the network, you need to think about all these different things. It's much easier, I think, to keep the conversation on consensus focused purely on, is there a digest we commit to at this view or this height, and that's it, and then everyone else can do stuff based on that. And so, for this, all the talks here already have focused a ton on this. I don't feel the need to spend much time here, but imagine that you can pick some gadget. They all have very different trade-offs, properties, fault tolerance, and then kind of hook it up. But what you're ultimately trying to get is some way to have agreement, and that agreement typically comes from people communicating on the network layer. Now, the one thing I do really want to call out that has been alluded to a few times here, the problem is that a lot of the papers that you read assume eventual message delivery. Real networks do not have that guarantee. So you have to deal with that problem, either by creating that abstraction somehow in the node to say, well, we want to implement the consensus protocol exactly as is, and use some sort of network abstraction that lives over this, that somehow guarantees that every message that I want to send as a node will eventually be acknowledged by every other participant. Or you do what everyone seems to do, which is tweak it a little bit, tweak the papers a bit, to get them to work in some way over an unreliable network. Now, there's a huge question for this, I think, for this group of like how to think about this problem. There's been some papers that have attempted to reconcile this by like saying, can we create a paper about an abstraction that would give you the things you need to basically just implement the consensus protocols as is. The problem is all of those constructions end up having quite a bit of overhead if you think about it, right? Because it's like, all right, now we need to track all the acknowledgments of all the messages that we're going to send, and then what happens if a peer decides that they don't want to keep acknowledging our messages? Do we have some sort of bound? Well, as soon as you do that, it's all broken again. So, because they could just be offline, there could be just some bug. And so there becomes an interesting question of like how you actually want to turn what is like a consensus paper that assumes this eventual delivery into how you reconcile that with a lossy network with limited RAM. And so that to me is unfortunately where I see a lot of people get stuck, is how to actually adopt these things safely. Yeah, Kartik.
So what is the percentage of drops that we release?
I think actually Alberto made a good mention of this yesterday. It's not like during steady state you'll see like a ton of drops. Like usually you'll have a connection that's live for quite some time actually. It is what happens on the edges. So like people are restarting their nodes. There's like a node upgrade, software upgrade where you'll take your node offline for a few hours. There'll be like some outage in AWS where like periodically your nodes will go down for a few hours, or like the network will be partially partitioned. But very rarely do you see steady state drops, especially if you use something like TCP underneath, which like eventually makes sure that all messages in the stream do get delivered. Yeah.
So I guess in that sense, it is, we don't even know if it is. So these drops are not random in that sense.
No, it's just you basically just the guarantee that you're like that certificate you broadcast or that vote you broadcast is going to get to everybody. Is often too strong of an assumption unless you want to add retries on the sender side. And whether or not that's virtualized for you So like once you click send in the consensus protocol, it's eventually going to get there. Or you want to layer that, or basically bubble that complexity up to consensus itself, becomes, at least in the conversations I've had over the last few years, like the core complexity for most teams is how to actually think about that. Because they look at some paper and they're like, this is cool, okay, but I can't implement it. I don't know how to implement this. This is not possible with the tools I have. For example, and I think this is the thing that keeps us grounded is consensus, when you implement it, it's a lot about what happens now. You don't kind of care about like that view that was finalized 10 ago. You're willing to drop actually everything that has to do with that. It's irrelevant to you. And so what we'll do at many layers of the stack is under load, actually we'll just shed messages to save RAM. So like even if you have a stable connection with someone and you're sending a certificate, you may just drop that if you determine it's no longer useful. And so often we get into this point of reconciling what is efficient for the node to actually do versus what does the theory say is like how we should actually behave. Like everyone talks about simplex, right? Like simplex assumes we're passing around the whole log every vote. I don't think anyone that uses simplex does that. So there's a gap between that and what people actually implement. And I just want to call out that gap in many cases can be very big. And usually the bugs are not in like the consensus paper, the bugs are in the gap. Yeah.
I think the way I try to simplify it is you can think of this as some sort of a temporary failure of the board.
Yep.
We just that at both levels.
Yep.
When it's a failure, I will think of it as counting it towards the F, at least temporarily. And once it gets back,
Yeah.
it is back to being on the spot.
Yeah. I think, unfortunately, you often, in some of these edge cases, will have failures greater than F, and the network has to recover somehow. And the recovery step is often, if you do nothing else, will just never recover. So you end up having to like resend some messages. So for example, in simplex, what we do is if you're stuck like for more than some configurable amount of time, you'll resend the certificate that caused you to enter that view. That almost works every time. And then there's some extra stuff you have to do in the cases that doesn't work, but yeah.
I mean, at least from a theoretical perspective, I think there's this understanding of the difference between the consensus part and the learning part.
Yeah.
And if you go back to the 1990s KBFT, you look at, it's called state transfer, right? There's a lot of literature.
Yeah.
Maybe state synchronization, different, but like,
Yeah.
this is a well-studied problem,
Yeah.
right? With a lot of protocols, a lot of well-established
Yeah.
techniques. So, yeah, I would say,
Yeah.
I understand like the 30 years of engineering. Forget the theory.
Yeah.
Like just how do you do learning? Like,
Yeah.
learning means that something was already agreed on. You need to kind of get back to. There's a lot.
Yeah.
Of,
Yeah. I mean,
and then my second comment is around like. This goes back to like why not just use TCP? I mean, this is not getting okay. I mean, okay, so if you care about like what happened 20 views ago,
Yep.
then that's a learning problem. If you care about what happened, 3 views ago,
Yep.
right, then it's like, so why didn't we use TCP? Like, is this premature optimization of some networking layer that's trying to get crank another 5% performance?
no. So I mean, for example, in what we do, we use TCP for everything. The problem is those streams can get backlogged, and you have to determine what you want to do at that point. Because I'm not going to let you just let me store arbitrary memory. And if consensus continues to run, I have to do something about that. And like TCP will only let you send so fast. So what do you do?
Oh, then you move to state transfer. Yeah.
Yeah.
So,
So I mean,
that's kind of
yeah.
okay. So I'm saying like that's what you do, right?
Yeah.
So you use TCP first of all. Right?
Yep.
Like you can do UDP fine.
Yeah.
We can do that as well. Like that's
Yeah.
a separate discussion.
Yeah.
But then if you fall back too much, right, then there's a different problem. Your
Yeah.
problem is learning.
Yeah. Well, I mean,
You're not participating in consensus. You're not helping, right? You're doing damage in consensus.
I think my claim would be that TCP does not prevent you from the learning problem.
Of course.
Yeah. And so I think it's just the balance between those and like how frequently you maybe want to do learning. Because if you do like a pure UDP thing where you just assume nothing about any of the messages that are sent to you, and then you're constant, like some networks do that, right?
But this is
Yeah.
well entrenched into
Yeah.
like, PBFD. They have checkpoints.
Yeah.
That kind of tells you what is the boundary that you want to start learning
Yep.
versus participating in consensus.
Yeah. So, yeah, I think at least in the conversations we have, I would say people do not appreciate maybe the depth of literature there, and so maybe a great topic for your blog. Yeah. Yeah.
Yeah, I think you are aware of the concept of stubborn channels, right?
Oh, what'd you say?
Stubborn channels? You know this concept?
Maybe by like what it does, but not the
Essentially,
name.
you'll continue sending the same message until
Sure.
the condition is set.
Yeah.
In practice, this works, right? And if you have some semantic knowledge, so like you say, the consensus, you don't care about this from the networks around.
Yeah.
You just say, keep resending this message until some state transition.
Yeah.
And keep sending the same every 5 seconds.
Sure.
You say, right? So
Yeah.
do you have something for that? Because I think this is the real solution. This is not working.
Usually you can do better than that if you have a better like understanding of what the consensus is actually doing. Like you really want to make sure people can land on the same fork and have enough certificates to vote on the same fork. And so there's some ways that you would, there's a lot of well-established theories for like trying to understand how to make sure people have enough knowledge to land on the same fork. So the problem ultimately can be simplified, we find, or like not simplified, optimized by not just sending the same message again and again, but sending what would help the most.
Yeah, but this is the semantic part. So you can continue sending your vote,
Yeah.
you get a certificate. At this point, you stop sending your vote and you send the certificate, right?
Yes. So
This
that's
is the semantic part.
Yeah, so it depends on depending on what your consensus construction is, like how many views you're doing that for, like how many heights. There's a lot we can go into. I think it'd be good to get into the next layers of the stack, and then I think that helps to inform maybe how you want to think about the problems in this layer. So you asked a question on like the open versus authenticated P2P and what it gives you, especially when you can connect to specific folks. So this is actually one of the things that led to one of our what felt like our easiest optimizations, actually. So I think when people think about gossip and P2P networks, they think about the image on the left, which is like people are kind of randomly connected. At least that's how like ETH or like Bitcoin work. And then you have something which is not like every message flows through me, but from my perspective, this is what the network looks like to me, is I'm connected directly to the participants I care about. And where this can come in is like when you think about how gossip actually works and how to then like kind of measure who is a healthy peer for you and who is not. So if you have an open P2P network where there's like a mesh like this, every message that you propagate, you have to verify before you'll send along. And if you don't, then the peer that sent it to you, you should assume is malicious or something like that. And if where this can come in handy is really in the consensus layer, because you can buffer signature verification really efficiently. So what we do, for example, in Simplex is we actually only do one batch signature verification per view per certificate. And so we can run a network with like, thousands of validators with like a couple 100 millisecond view latency and on like 2 or 4 cores. You need that authentication though to be able to do that, because if someone sends you an invalid signature, you obviously don't want to let them keep doing that, because to determine who sent the invalid message, you have to do some form of bisection to find it. And that can be much slower than obviously the batch or even verifying every message. And so you then have to assume there's some number of views per epoch that you can block somebody, and then once they're blocked, you're not going to have to do more of these like bisection games. Yeah.
I mean, when you say that, it seems crazy, because every time I tell that to people, they always like that sort of conversation, but we all do that. I mean, it makes lots of sense, right? Because what actually happens before the signatures, I don't know if you are the same, but we also have a very cheaply authenticated channel using only symmetric keys.
Yep.
Right? So effectively, if you send me through that channel a signature that's invalid, I know that I should not talk to you
ever again.
Right? So
Or over for 4 hours or something. Yeah. So I think what I've seen a lot of is different networks that run in the proof of stake setting that have not quite adopted or like updated their P2P model, maybe to reflect some of the work they're already doing on the layers above, where you could then unlock a number of different optimizations. But yeah, I actually think the authenticated is most useful just for being able to block people, and then you just kind of don't even attempt to talk to them for some period of time. You gotta be careful with that, because if there's a bug and you block more than F, you'll stop. So hopefully you don't have a bug that affects more than F, but yeah. The other one that fits into that very clearly is like how you think about selecting the cryptography that you use. So I think we'll credit like Justin Drake with really bringing us back to some of the BLS stuff, and maybe some of the Dfinity folks as well, who I know are like really early adopters, and a lot of that for the blockchain setting. I'll get into this later, but really, like with proof of stake systems, you get these really nice certificates around different sort of finalization conditions. And those certificates, in my opinion, are criminally underutilized throughout the stack and the layers above. And so The problem so if you do something like aggregate BLS, you get some really nice properties, most of which run in tension with the idea that you then have to still synchronize who the active committee is to do verification at all the layers above. So if you wanted to, let's say, verify messages that come out of ETH2 on another chain, you have to synchronize all of the participants on the other chain that are verifying it, whether you do that with like some sort of ZK mechanism or like Snark, or you do it with some sort of direct communication. You have to track who the signers are to actually verify messages. And so one of the cool things about Threshold, if you're willing to accept some of its properties, is you have a static key, and at least in our case, is like 96 bytes, that allows you then to verify any of the consensus certificates that come out very easily on other chains or in the browser, which we'll get into. The other thing that has become a lot of a topic lately is whether or not your scheme is post-quantum secure. And I think there's a lot of teams doing great work trying to make some really practical schemes for this. I'm not aware of any like post-quantum threshold scheme yet, but there are some interesting candidates for aggregation. The other one that I'll touch on real briefly is leader selection. So this is the other thing you kind of think about in the consensus world a lot, is who actually determines, or like who proposes the blocks, what frequency, and like kind of how they're actually selected. So this obviously varies quite a bit if it's a DAG versus, I think maybe not as much as people think, given your talk yesterday, but at least in our case, we've modified simplex to emit a VRF for every view, a VRF result, so then the leader election is only known one view ahead, which can help with targeted DOS resistance, but has the unfortunate consequence that if you're trying to submit transactions into the network, you don't actually know where to submit them until right at that moment. So you have to either submit to everybody, or you have to be very quick getting the transactions to the right person. So different teams will do different stuff, usually on some range between VRF and round robin of some variety, and maybe a round robin seeded by an epoch VRF or something like that. Yeah.
So in practical systems like Algorand, the VRF is weighted with a stake. So for each algo you can run VRF. How do you implement it?
Ours, we use so we have threshold cryptography in consensus itself. And so we have two signatures that actually come out of a certificate, one that is over the actual digest in the block, and then one that is over the view. And so you'll send partial signatures over the view in every view, and so it doesn't matter whether or not you notarize, nullify, or finalize. You'll eventually have enough to derive basically one threshold signature over that view, and then you can use that basically as your coin, your random coin, to kind of determine how to order the next leader. Yeah. So don't take my word for it. We actually have a demo online. I don't think it's going to work, but well, it'll work, but I'm not going to click it here. But in this demo, we're running threshold simplex on a global network, and then in your browser, we have WASM cryptography running the threshold verifier, and so we have a static network key, and then everything that shows up in your browser is verified using that static threshold key. So don't take my word for it. It's very possible. All the code's open. Huge credit to the people behind the BLAST library, I would say, and the work ETH2 has done to really productionize those systems. But Threshold, I think it's a wrap sometimes for being impractical on larger and larger networks, and I think I hope to dispel that myth because it's very practical. Yeah.
Sort of follow up on the last question, is it state-weighted threshold?
So we focus on this for Threshold only on the uniform weighted case. There's some very active research in trying to make it work well for varying weights, but it dramatically complicates things. I think Aptos has a pretty good construction for like randomness from like a, I forgot the name of the paper, but there was a paper like 2 or 3 years ago where they have like a VRF that's generated where participants have different weights, and they have a pretty nice construction for that. But it does not have support for resharing. So every epoch you have a separate key that you verify against. What we care a lot about is maintaining the same static key over epochs. And so in that construction, if you want to have something that you can diagram and talk to like a security reviewer about, you're going to want to stick to the uniform weighted case for that, at least in the threshold state right now. Yeah.
So should I think about the canonical case here being very high minimum weight to be able to stay so both count values and most weight? also does as much as you need across the state?
So this is research we're actively doing with a few folks on like how to think about how you want to set up the actual economics of a proof of stake network under this scenario. I think some of the work that came out of like proof of governance, if you've followed that line of work the last few years, is really cool, where you have like a governance vote that the whole network participates in, and then you elect some fixed number of participants, all paid the same. It comes from the idea that if you have proof of stake, especially DPoS, eventually that's going to devolve into liquid staking. And eventually that's going to devolve into like some pretty big cabals of people. Basically everyone is always going to liquid stake. And so in the case of that, what if we just skip that whole loop and instead just paid some fixed set of validators, some fixed costs, and maybe gave them a little bit more based on what their proposal outcomes were? Works really well with something like this. But if you wanted to just map today like an existing proof of stake system that has like some range of weights, and then that's how you got selected, it would be more difficult. So we support, and I don't want to make this talk about us particularly, but like we support a number of different schemes. So like whether that be like aggregate BLS, threshold BLS, or even ED and like SecP keys. So you can kind of pick, and then if you don't want threshold, then you can do different weights if you want to. And so think of it in the uniform case, we just give every participant in threshold a weight of 1, and then everyone else, you can just modify that if you wanted to in different systems, But again, it comes down to like how you think about the P2P, balancing the P2P, like the rate limits there. Do you want to vary those based on the weights of the participants above? Should you or not? I don't know. I think there's a lot of open questions on like what we should do there, really. Yeah, but so far people have been satisfied with uniform weights, and it simplifies quite a bit in terms of network management at least. Okay, so you got these digests, and now this comes into your kind of question, which is like how do you actually then emit some sort of like contiguous log over the results of consensus? And so this is where you actually figure out how do you fill gaps in consensus that maybe you have locally? How do you then also get the blocks that are associated with those digests or whatever the payload data is? And I think I wanted to give a particular shout out to Joachim here, because some of his work, I think, on like the permissioned to permissionless consensus paper does a really nice job of also talking about how you would, and also Andy. Success has many fathers, right? That's what they say? All right. So I think some people also, when you actually like document a consensus protocol, right, it's over typically like a static set of participants over like some run of views. I think for a practitioner or an engineer, the question very quickly becomes, well, what do I do when I change that? Do I try to mod that consensus mechanism itself to somehow allow me to change it? Which I have seen civilized constructions that do this, just to be clear. So like it's not like an obvious thing that you wouldn't do this, like it can be a thing people do. Or do you just take a construction and then find a way to somehow safely transition into some sort of other, after some reconfiguration point, into maybe another epoch or era or whatever you would call it. And so, there's some pretty clean work here, which ultimately boils down to after some number of finalized blocks, next epoch. And so if you have more finalized blocks than that amount in a particular epoch, you just cut them off as if they never happened. So maybe you want to propose the same thing again and again at the end of the epoch so you don't waste any work. But that ends up being a really clean solution for any consensus protocol you want to put in a particular epoch. And I would strongly encourage you to use that trick rather than trying to somehow embed some sort of epoch reconfiguration logic into your special consensus protocol. I think what comes down to this, though, as like what the actual log is here is the log pristine? So like, is the log only containing valid state transitions, or does it include anything that people want to submit? So in some cases, your execution model, or like what you're doing on admission, may not permit you to actually have a pristine log because you don't have synchronization of state at the time that you would admit a transaction. And for some things that can be nice, because in theory, you should be able to go higher throughput if you can kind of put more data into the system, and maybe you're willing to make a trade-off there. Most of the chains you know today do try to maintain a pristine log where you only include transactions in the log that are valid. The benefit of that is if you have certificates over the pristine log, you can just use those certificates directly to check different information in the log as a light client. If you don't have that, you need to then have another layer of certificates on top of that you can then use to basically check or like prove data against verified information, maybe that's emitted deterministically off of the log. So we'll go into that.
What's the difference between a log and a pristine log?
So the way and there may be better terminology for this, so you'll have to excuse me on that one, but like the way I think about it is a pristine log only has correct state transitions in it. So like during the voting process, you'll actually check whether or not the state transitions in like the potential block candidate or like digest are valid, given the rules of the state transition function, versus just agreement. So most people do that. So you're gonna love this next section yeah.
What's the valid state transition?
What'd you say?
What is a valid state transition? Any state transition is a valid state transition. You can stay in the same place.
No, I disagree with that. Like you have an account, does it spend more than it has?
But in this case, the transaction say if I have no funds, do that. Otherwise, stay where we are.
Yes, I mean, so if you have an account and it can do something and it does that thing that's valid.
Everything's valid.
No. So now if you have an account that doesn't exist and now it's spending $50 and you have a stable coin, that's not valid.
Because fading is a valid state transition.
Well, it depends. So like if you have no fees to pay, do you want that in your log? I don't know. Some people would say no, because that's a huge waste of bandwidth. Some people would say yes, because then you don't have to do as much on the validation side as consensus moves forward. Most chains, though, will check that, and they will not permit that transaction to enter the log. Like, if you look at an ETH block, find me an ETH block that it contains that transaction. There is none. Every block only includes transactions that can pay fees. That transaction may fail when it's executed, but it can pay fees. So it can still pay fees. You're not including transactions that can't pay fees. What? Yes, other signed. There's a few different things. So there's like syntactic validation, semantic validation, and then how you define that state transition function. Yeah. So how that's layered and like how you actually then end up like broadcasting data, there's a few different things. You would think about traditional state machine replication where you like build a block, replicate that through the network, verify the block, build on that. You can only build on that maybe once you've verified that block. Again, this depends on the structure of the log. This is how it was done for a while. Then you have something like streaming state machine replication, where you'll start to actually build the block and start to replicate it before you finish building the whole block. The benefit of this is that you can start to verify it before the whole block is built. So like Solana, for example, does this in its current form. And what it lets you do is start the verification process because you're checking all these state transitions during the block. And then what I think some DAGs have done, and like some of the Narwhal Tusk line of work, is that you broadcast and do all of this concurrently and then later on linearize it. I think as you think about these systems, these three decisions have huge trade-offs and implications on how you actually think about constructing the system. And I think one topic I want to focus on is really, it comes back to this question, which is admission is hard and a hard problem to solve in a world where you don't actually have a view of state of who can pay fees. Because you can have data in a block that maybe you should have given to someone that could pay fees versus someone that couldn't. And ultimately, if you send the right sequence of transactions that are invalid, you can fill all your blocks with invalid stuff, and then as a result, kind of choke the network from honest participants being able to play. So the simplest one to think about is you have duplicate transactions that you send. Let's say, imagine this case where validators are in some sort of DAG construction where they can all emit some sort of block data. And I have an account. Well, what I could do is just send the same transactions to each validator, and they don't communicate when they pack their blocks or their vertices. And so they could all include the exact same data. Another problem that can happen is conflicting transactions. So what if I have, most people have used Ethereum where you have a transaction with the nonce for an account. What if I send the same transaction or different transactions with the same nonce to different validators? So they're actually like different transaction hashes, but they have the same knots. And so both of them could not be executed, at least in most execution models. Who would pay fees, or like how would the fees be actually pulled from that? And then the last one is also fund exhaustion. So what if I have a bunch of transactions I submit that all look valid, but it turns out the first one actually exhausts all my fees. And so then the other subsequent ones that I submit no longer can actually pay fees or be executed. And so these can get really bad if you combine these attacks, where you basically send, every account sends like a duplicate, a conflicting transaction, and fund exhaustion. You can take what is a lot of bandwidth and make it a lot of unuseful bandwidth. And so when you're thinking about how to actually validate what goes in the log, it becomes a very challenging problem in practice to think about how to build an application on this model, because what on paper may seem like great bandwidth can ultimately be governed by the efficiency of how you determine what goes in that log and then how that actually is useful in the application. So some people that have started to reconcile this have started to do some sort of like fee reservation mechanic, what you would almost call like an account fraud proof, which is the idea that you lock up some amount of funds as like a reserve balance of some variety. And then once it's reserved, each validator knows how many transactions they should admit because they know they're going to get paid. And they know that they're going to stuff the block or vertex with something that's actually going to be something that gets them some fees or the network some fees. And the goal, right, is how many transactions that can pay fees you want in your blocks. Now that may be different based on what your network is, but usually that's the goal here. And so there's a lot of different research going into how exactly to do this. We actually filmed a podcast with Max and Ashwin from Anza talking about Constellation and got into some of these topics. So if you're curious about this, I would recommend listening to that. Another topic to think about as it pertains to the log is this conversation between extractable SMR and then SMR. And the idea for that is something that really comes into like, what are the expectations of how you locally learn about what the log is? So do you have to go fetch data? Is it just available because you know that some number of honest participants have a copy of it? Or is it something where all honest participants will eventually hear about what that data is? And so when you look at things in this setting, something like a DEG versus something like a balanced broadcast network with like erasure-coded broadcast have very different properties. So a lot of the constructions of a log where you do like pre-dissemination before agreement assume that you get a certificate from 2F+1 parties. And so you may have to go fetch some of the dependencies in the log to actually continue to linearize or process the chain. And so when you're actually processing things or admitting people, you may on the hot path have to go fetch stuff from other people. And so depending on the resilience you want and the honesty of the participants in the network, you may choose to balance between extractable SMR or SMR here. So I think we're what's the time check actually?
About 12 minutes.
12 minutes, okay. So, all right, so the last one is once you have the log, is what you want to think about is how to apply some sort of function over that to derive the state for all the participants. So I pull this up because this is MakerDAO's diagram for how their contracts work. The state transition function can obviously be pretty complicated. And this is just one smart contract on Ethereum, right? And so as you think about how to actually efficiently process data in the log, there's a ton of different research, I think, actively going on between how you can like pipeline things and start to process things. So like a few papers I'll bring up if you're curious. One is from the Aptos folks where they kind of lay out how you would try to achieve optimal blockchain latency by like sequencing all of these steps in the right order. So like where you have the dissemination, the ordering, and then you execute, and then the tough part with this is how you feed back into the system. So if you are executing something that obviously is removing fees from the balance of some accounts, how do you work that feedback into what you're willing to disseminate? It becomes this admission problem. And so it can become interesting to do safely and securely because you want to propagate that feedback up to make sure you actually pack blocks that have value. Or have some way to prevent like spam from taking over the network, or really what you care about is spam that doesn't pay fees. Another one that's really interesting is from the Mist and Labs folks, which is how you actually distribute maybe the load of execution across multiple nodes. So instead of thinking about a validator as like a single logical node, what if you had like a cluster of execution workers that you could split the work around? Because all you really care about at the end is like, is this block valid? Or maybe like just making sure you have a deterministic list of what transactions in that log are valid. It really doesn't need to be all on the same node. And if you take it to its logical conclusion, well, what if we have these really efficient ways to propagate data through the network, but we actually can't keep up with the state transitions? So what if instead of thinking about a validator as a single node, you think about it as a cluster? And so that's a really interesting paper that talks about some of the implications of that. Another thing you'll hear about in this as well is this notion of whether or not you should authenticate state or not. So some people have taken the conclusion that, well, so to back up, you have some state on the network. This is like the balance of the accounts, what they're doing. Maybe they're nonces, maybe some other stuff like smart contract state that's not specific to a specific account. And so you have this, think of it as like a big key value store usually. So when you're a new node in the network and you want to process state transition functions, or like the state transition function, you need to have the same key value map as everybody else. Otherwise, you'll disagree on the state of the chain after you process the log. So first, how do you get that key value map if you're a new node in the network? Do you just ask some other validator, like, can I have a copy of your database? Maybe that's part of the system, and so like they'll snapshot what they have periodically, and then as a new node, you can like go to some endpoint to get it. Or maybe once you're connected over the P2P network we talked about, you can somehow request it from other people. Maybe they'll send you a zip or something like that. Or if you apply a little bit more structure to the state, what we would call, at least what most people call authenticating the state, you can get efficient, basically proofs of parts of the state from different peers, and then know that what you're requesting is actually part of the active state. A huge win here is that if you do authenticate the state, it's also easy for someone outside of the chain, if they have a consensus certificate, to verify that some state has been agreed upon, which is huge, right? Like if you want to know your balance, for example, when you go on an API node, it'd be great to know that like consensus is convincing you that that's your balance, not some API provider. And so this ultimately becomes a thing a lot of people today will disagree on whether or not to authenticate state, and then if they do authenticate state, how frequently do you authenticate state? Do you try to generate some sort of root every block? And so we're very interested in like the authenticated log structure. So we have like MMRs or like Merkle Mountain Ranges. And if you've heard of a database called QMDB, very much in that line of research. Ethereum uses something called the Merkle Patricia tree, which is like a radix tree, which can be, a lot of people spent a lot of time optimizing, but can be difficult to optimize. And then the last one, and then I'll take your question here, is lattice hashes, which has been something that the Onta team has been experimenting with. And this came out of Meta. It's a pretty cool construction where you have this basically an accumulator that you can add and remove like state entries from. And so if I give you a snapshot, let's say, and you apply everything that's active in that snapshot, we'll agree on this lattice hash, even though I can't prove anything about any specific key in the lattice hash. But I can at least know that this whole chunk of things we agree on, which if you're syncing a node and that's all you care about, can be a pretty nice compromise because this is pretty efficient to operate. Yeah.
So on the previous slide, so what is your view about it? Because everybody is agreed, as you said, right? So do you manage to build one big authenticated log at speeds?
Yep.
What do you end up choosing it in?
So for us, we do this, and we've spent a lot of time optimizing it. Yeah.
And you do it immediately, right after consensus, or checkpoint by checkpoint?
So today, so I'll get into this in the later slides. I'm not sure we're going to have enough time to give it the detail it deserves, but we're very interested in making anything that we do very light client friendly.
Yeah.
And so what we care about is time to proof. So we care about having a checkpoint every block, and we have optimized a lot to make that happen. But it's the way that we do that is it's all append only. So we never modify anything in place on disk, never. And so then it turns out there's a number of tricks. We have, I think, 6 blogs about how we turn a normal Merkle Mountain Range into this really performant state database, and like using a append-only disk with all sorts of ways you actually lay out the MMR proof structure and like how you actually do. So in MMRs, you can think of it the standard case where it's like you just list all the transactions, easy. Next one would be how you actually turn it into like a key value store. And what it ultimately you do is you synchronize compaction at different blocks, so move data with some sort of frequency to the tip. And then you can get all sorts of different properties by maybe linking keys lexigraphically as well. So then you can prove that something isn't in a range if you wanted to do an exclusion proof. And then on top of that, you can layer a bitmap to actually show that a key is also current or not, given some root.
Right.
So there's these kind of like layers of sophistication you can add. Yeah.
So your pipeline is effectively execution happens, authenticated data structure is built, incrementally it is updated in a smart way so you don't rewrite this all the times.
Yep.
And you keep doing as frequently as possible. And the final route, do you pipe it back through consensus?
So we do it fast enough where it actually goes, this is all done during the verify step, like before you vote. Okay. So that'd be the dumbest version. We have a modded version of Simplex where it looks a lot more like dispersed Simplex, where we have deferred execution, so you actually vote on the initial agreement, and then before you vote finalize, you have the option to decide to time out instead, and then you can skip. So we actually pretty efficiently pipeline the construction of that with the voting on the network. Yeah, I think what I would say is like, just writing to disk is very fast. And so if you can reorient the whole database around that concept, you can work around some of these other issues. And I think one thing that's actually really cool that we found is because compaction is synchronized and you have to move things to the tip anyways, you can do some really cool stuff with basically like state fees for no cost, because you're already moving the data and rewriting it anyways. Or because it's an MMR and like the current root authenticates the whole history, you can just not move it and then very efficiently allow people to basically re-inject their state back in, because the current root attests to the whole history of the log. So I think a lot of people talk about how you can have like this hot and cold section of like on-chain state, and as you reach some scale, like you have no option, because you need to have uniform access to state to prevent a DOS. Otherwise, if you can't fit into cache, like if anyone knows what Zen is, you know what this is about. Yeah, the cool thing is with this kind of structure, you can have things just gracefully fall out and then with no overhead be able to prove things back in. We haven't done that yet, but that's something that we're very interested in doing.
Your first thing is the reason why we built Highlander instead of RocksDB as a backend, exactly for the reason you said. So we're roughly going to the
Yeah, so I think that the other difference is we don't actually ever maintain, at least we don't have one, a generic key value store.
Okay.
So we actually only abstract this as like a journal concept. And then for any indexing, we do like efficient indexing with like multi-maps in memory. So we don't actually have like a key index on disk. So yours is probably a little bit more powerful, and we've decided to really try and strip it down to the dumbest thing. But yeah, go ahead.
I have too many things.
Well, there's a lot, I'm sure. The whole point of this talk is like kind of a smorgasbord of like all the topics that I think I've heard a lot of people talk about, and it's more of like a cheat sheet if you're thinking about engineering a blockchain, how you want to think about the different components.
Yeah, so I mean, maybe I'll just say that at a high level, I think you're opening up kind of the question of what is the outcome of the system in terms of the read path. Read path, okay, you said extractable SMR versus SMR. I think that's kind of just too coarse of a and now you're like saying, oh, should it be like authenticate or not? I actually think it's much more richer landscape. Anyway, that's kind of high level.
I think I could go over this for the whole 4 days if we wanted to kind of get this survey. So my hope is to try and kind of direct people towards maybe a direction of how you would want to do this, rather than maybe the full landscape of opportunities maybe available to you.
Right, so the way you would want to do it, right? For example, what you didn't mention is I might want to see how much I have in my account. Right? So that's like a new type of indexing.
Yeah.
It's not I want to see what happened in block 17. Who cares?
Sure.
Or like was this key touched in block 17? I don't care about that. I want to know my latest value in my account. Right. So that's a new type of indexing. So that's why I'm just saying like there's a whole indexing engine that you could imagine building, and you might want to get an authenticated answer to that. Right?
Yeah. So the authentication, I think, That's usually for people outside of the chain or people synchronizing the chain is how we think about it. But in the chain itself, when you're actually processing the blocks, we don't touch any of the authentication. Like you kind of assume you get to a point where you have all the state that's currently represented by the tip. Yeah.
That's a recap, right? The
Yeah.
recap is like if you are bridging
Yep.
and you want to get an authenticated statement that
Yep.
my account
Yes.
has money. Not that block 17 had something.
Yes.
Because
Yes.
That doesn't mean a lot.
Yes.
Sometimes it does.
Yeah.
But if you need to, get
Yeah.
a authenticated proof of consensus, then my account at this point in time had enough
Yeah.
funds, right? That's something that's valuable
Yeah.
for something.
Yeah, so
And by the way, if you overdo this for everything, then you're just wasting a lot of indexing work.
Yes.
Right? So you have to do this
Yeah.
at the price. So anyway.
So funny enough, the way the bridge works for a lot of egress is they're one-way bits. So it's actually usually never checking your account state now. It actually is almost always a bit that can go and say like, oh, I've emitted this amount, and then that stays forever in state. And that's horrible, but that's what happens. And so then you just need to check something, and then usually some routes forward have that, and you're willing to do that. Because again, sometimes in consensus, you may not have a direct finalization. And so you do oftentimes want to use authenticated structures that can give you the ability to get some sort of maybe history if you want to. But at least today, all chains I know that have some form of egress bridging have like a section of state that basically is immutable, and once you emit something, it just stays there forever. So like in the Cosmos SDK, like for IBC, one way. So settle with that how you want to. Yeah, I think the last one I just wanted to touch on to kind of wrap things up is everything I've described to you is not how the average person actually interacts with anything. There's an API. And so that API is your proxy for both how you get things in and how you get things out. And today, I would say 99.9% of all the traffic blindly trusts this API with their life. And I think that's a shame. We do all this work on all these layers beneath it to secure it and have all these people, but ultimately that API can tell you whatever it wants. And so the reason why I bring this up is that in some of these new networks, these like higher throughput modern networks, you do not have the ability to join and run a node because the overhead on the validators is not something that you just want to pay for. So either you just connect to that API and be like, well, hope I'm not a good provider, and if I ever find out they gave me the wrong data, I'm going to switch providers. But oftentimes in the moment, you're not going to know. And I think there have been a number of hacks lately, and increasingly so, of people kind of trusting these APIs or a quorum of APIs instead of the actual consensus itself. And so everything that we've done up to this point, we have oriented around the idea that we can basically emit succinct light clients all the way to the user. And so what we care about so you mentioned there's like a huge breadth of decisions. What we care about ultimately is what's the throughput we can get that still gives us very quick time to proof, that I can give you a full certificate that this is the actual data you care about, and then indexing enough that's useful to you. And so there's a great blog, if you want to hear someone rant about this, which is Moxie, who created Signal, called My First Impressions of Web3, and it's hilarious. But it's a good read if you think we've got it all figured out, because this is today still how it works. And so what he boils it down to, and I think is a good close, is we need to accept not everyone's going to run their own servers. So can we somehow distribute trust without having to distribute the infrastructure? And the two, can we reduce the burden of building software? Well, fortunately, number two is taken care of, so we're good there. But number one, we have the technology. So like, this is what we should be doing. And so I ran out of time, but I was going to show you a live demo of our thing that's going to release early next week, where we have the whole system running at basically 50K TPS with 300 millisecond finality with like 500 millisecond end-to-end latency, but with proofs. And so we'll see if this actually works. Oh yeah, cool. So transactions are pass keys. So we basically, the signatures, so we actually verify directly WebAuthn on chain. So there's no trusted execution environments anywhere. You just click a thing and you sign it. And then when you submit a transaction, it'll show up on chain. And then we also get a certificate from consensus and a proof of the transaction's inclusion in consensus in the finalized state. So here I submit a few transactions. I got obsessed with the Touch ID thing. It's fun to click. And then I took, let's say, my account here and looked it up. And so imagine an account page, again, all secured by certificates and state proofs. So everything that we show here, we have a proof that was actually included in the finalized history of the chain, and then your state proof at a particular location. I refresh it, and you can do whatever.
You're proving that nothing else happens in this range also?
No. So we don't prove completeness, but just that at least what we show you is correct. So I think today it's easy to take a metadata layer of some kind that's untrusted to like give you insights of like what to fetch. And then once you have that, anything that we show you, we can ground in truth. But showing completeness, I think, is a much harder problem, at least for like the history of an account or something like that. This would come into your indexing question. You could do that. It's just a matter of if you want to pay for that in the chain. Because again, we want to agree on this over consensus. And so that would mean all the validators obviously have to process whatever that is. So some people we have experimenting with this to see if they can basically make an order book this way. And then in that case, they actually do try to do completeness and like have the ticks and like even index a bit over it. If the database is fast enough, I would love to see it. That would be my response to that. Yeah. And so how we fit into this, and this is it. We think blockchains are going from this like application to virtual machine managed resources to an application determining much more of each layer of the stack. And our job is, can we make this simpler and cheaper so that we get, hopefully in crypto, richer applications? That's it. Thanks. I think I went over time, so I don't know if we have time for questions, but
Maybe like 2 or 3.
yeah. I think there's one back there. I don't know if someone can run a mic back there somehow.
Oh, thank you for the great talk. So I was interested in this post-quantum migration thing that you were talking about.
Yeah.
So there's many information security cases. There's one very recent paper that published in Columbia. So I know the efficiency matches the signature-based ones. Can you just try to replace your current signature-based simplex with published security ones? Is that can you tell me any business side thinkings of how the semantics of that go?
Yeah, so we when we designed this whole thing, we did not want to play favorites, put it that way. So we keep the signature component totally undefined. So anything that can give us a vote and anything that can give us like a certificate, we don't care. And so if you wanted to play around with different certificate schemes, like maybe there's like an additional like synchronization step, like where there's like, maybe you're using a scheme that has huge public keys and you have some other way to communicate the public keys so that maybe in the votes, you just use an index into the public key. So we open that up for development. So you basically have the whole core of Simplex that runs on top of the P2P that like eventually assembles a log. And then you can pick all of those layers underneath based on what your needs are. So there's actually a team, I forgot the name, they built a post-quantum implementation of all this already. And I think that there will be many more opportunities to come around as like NIST finalizes more schemes. I think we're very interested in finding a happy path for people to just kind of have a post-quantum secure thing. The problem, as we talked about though, is like all those layers underneath, right? Are those post-quantum? Those are also all pluggable, fortunately, but like it would be great to have schemes all the way up that let you kind of achieve the same security. Yeah.
So the protocol that I was talking about, it does not use any public key.
Oh.
It uses message authentication codes and peer-to-peer authentication. So maybe that is a little bit harder.
So, I mean, just to talk specifically about how this works right now, when messages come off the P2P layer, this part, we pass them into Simplex with the sender. So from that alone, you could determine it. The tough part is how you then get some sort of certificate and whether or not it's useful to you. I guess you would say, like, I mean, I'm not familiar enough with the scheme, but I'm assuming it's something like if enough people say that this person sent this, that then you like derive that there must exist some certificate of some variety or something like that. I think you'll get into a problem with how you think about those lossy channels, and you may have to deal with that. But yeah, right now it's like we give Simplex who sent the message, and then that's kind of, from there it's up to you to decide. Yeah.
So another question I had was based on the database we use for authenticated logs.
Yep.
So I know there have been Ethereum faces a lot of write amplification from their logs.dt database. Do you encounter the same problem, or do you have any other way?
So when I say we built it from scratch, we built it from scratch. So like it's all the way down to the kernel, like in file management, into a journal. So there's no write amplification when you write something. The only amplification is when you have to compact to the front of the log. But in terms of like everything along the way, 0. So you just have the log of key values and then everything else. Like so for example in ETH, right, at least the way it used to be, and this is, so I'll go through a very brief history, right? Used to be you had this tree, you would walk the tree to get your data, and then you would read at each step of that had layers of amplification into the LSM database. So like you're talking like 90 reads maybe from disk, serial reads to get one key. Then there was a snapshot, so you could get the key. That key still had the write amplification within LSM, so maybe 7 reads, and then you still have to read all the nodes to then generate the next route, which each one of those you should assume has like 7, but at least those can be done semi-parallel. You still have to build up. With our construction, you just have this log of key values, and then the really nice thing about the MMR is it's really efficient to hash because you just hash the right kind of pending side of things. And we have this blog we released last week where we talk about a new type of bagging scheme for how the hash is actually computed, which is isomorphic with the binary Merkle tree. So it ends up being extremely efficient to both generate and prove against. But ultimately, the way we've balanced it is a lot of that really hot stuff, like within the inner part of the tree, is in memory rather than on disk, and we think that that's the right balance for a high throughput chain. Yeah.
I'll check out your repo for more details about that.
Yeah, if anyone has any issues or PRs they want to open, it's all open source. Well, sorry.
All right, let's thank Patrick again.